All right, hello everybody. Welcome to the midterm review. We are just kicking off Module 5 this week. This marks, well, it is the midterm, so it marks the halfway point for our course. And so I've just got a few things here I want to go over, kind of review a bunch of the stuff that we've learned up to this point, and to get everyone ready to take the midterm and to be successful there. Let's kick this off. So the first thing that I wanted to look at is, so looking at the notion of like a population, all right, and kind of thinking about like what is statistics in general, like what is it for, what are we doing? So populations, so normally in statistics, we're trying to study something. There's some natural law that we're attempting to know more about or understand. And so you have this law, or whatever it is, whatever phenomenon it is that we're trying to understand, and it's going to apply to a group of people, okay? And then that group of people is going to be our population, right? Every person, every individual, all the people to whom this natural law applies is going to make up our population. And in statistics, it's really important that you are very careful how you define your population, because that's going to control the type of data you collect, who you sample, how you sample, and all kinds of different things that we'll get into in the next couple of weeks, actually, as we look more into like real statistical studies. We've gone over a lot of like basic definitions, but when you're looking at a population, right, it's a group of people to whom some natural law applies, and we're trying to figure out more about that natural law. Okay, the different types of data that we can collect. We had really great discussion on this. If you need to review more about this, go back to that discussion board and read over it. You have nominal, ordinal, ratio, interval data. So the things that I like about this is you can kind of see like a progression in the data that we're collecting, right? Nominal data is a data set that is not numeric in nature, and that has no natural order, like flavors of ice cream, or in a typical study you look at gender and race, and so these are things that differentiate things from each other, but there's no like hierarchy. There's no, for example, when you're looking at the flavors of ice cream, strawberry isn't better than chocolate, isn't better than vanilla, isn't better than pistachio, whatever. It's just you have just these flavors, and they are what they are. And there's no real way to numerically quantify them, so you can't make an order, right? So those things kind of fall into what's called nominal data. The next is ordinal data, and these are things that, again, they're not numerical in nature, but there is a natural order. So for example, like the degree that a person earns. You can have a high school degree, you can have a GED, you can have an associate's degree, a bachelor's degree, a master's degree, a PhD, an MDD, a law degree. So there are all kinds of different degrees, and there is a subtle inherent order to them, right? So somebody who has an associate's degree it's well recognized that they have more education than someone with just a high school diploma. Okay, so ordinal data applies to non-numerical quantities that have some type of natural order, and then the other thing about ordinal data is that there's not like a defined jump between, for example, so if we say, okay, you have a high school degree, then an associate's degree, then a bachelor's degree, then a bachelor's degree, the difference between an associate's degree and a high school diploma may or may not be the same as the difference between a bachelor's degree and a master's degree, right? The gap between those hierarchies, there's not a quantifiable difference there. You can't just say, oh yeah, uh, they're exactly, the gap is exactly the same. If you have an associate's degree versus a high school diploma, it's the exact same as having a master's degree versus a bachelor's degree. We can't say that. So that's the other thing about ordinal data, is that we don't know, there's no real solid definition between the gaps of these ordered quantities. So these top two are like non-numerical, but these bottom two, they are numerical. So you have a ratio and interval data. So with ratio data, you're looking at proportions. Okay, you were looking at given amounts of things, and so the thing with ratio data is, so one of the real differences between ratio and interval data is, what does 0 mean? And with ratio data, 0 stands for an absence of whatever quantity it is that we're measuring. So for example, height and weight are good indicators of of ratio data. For example, because if your height is 0, then you have no height and you don't exist. Same thing with, so that's a weird example. That's a weird example. But if something's height measured as 0, then that quantity, it would be 0, right? It wouldn't exist. And then the other thing is that with ratio, it doesn't really make sense to have a negative quantity with ratio data. You can't have a negative height. You can't have a negative weight. So you can kind of think of ratio in that way. Now, interval data is different because 0 doesn't necessarily mean that there's nothing, that there's an absence of whatever quantity it is that you're measuring. And negative numbers do make sense. And the example that is widely used for interval data is temperature, because 0 degrees Celsius or Fahrenheit doesn't mean that there is no temperature, that temperature doesn't exist. It's just a placeholder on the scale. And you can have negative temperatures, right? It can be negative 15 degrees Fahrenheit or negative 5 degrees Celsius. And it just means that that's a little bit colder than 0 degrees. The only temperature measurement that has a real 0 is Kelvin. So Kelvin wouldn't fit into interval, it would fit into ratio, because 0 degrees Kelvin is an absence of temperature. And if you've taken many science classes, you know that all temperature really is a measurement of how much the molecules are moving in a substance. So if the molecules aren't moving at all, they're completely still, the atoms, that would be 0 degrees Kelvin. And they have a correlation in Fahrenheit and Celsius, some like really big negative number. But that's, anyways, so that one would fit into ratio because it is an absence of the quantity. So anyways, so looking at those are our types of data and measurement. So let's move on. We'll talk more about them later. Okay, so frequency distribution tables. When we do a study, we're going to collect data, and we're going to have all kinds of data and things to look at. So I did give one example down here of, so if you look, right, these are colors. So frequency of colors in a bag of Skittles. And I've got all the colors labeled here. And you look at this and you're going to say, okay, This clearly is not ratio or interval data because you can't quantify purple or red or green or blue, but you can count the number of those things that exist. So frequency distribution tables, I mean, you normally wouldn't talk about them in terms of these types of data, but if they were to exist, it might look something like this chart here. And these data are nominal. But anyways, we're not really looking at that. But if we were to, it would look something like that. These other things. So let's take a look at this one. Okay. So I have this frequency distribution table. I want you to notice a few things. Now these include tally marks, and a lot of the times we're not going to see that in a standard graph. They're just not going to put that there. So you can kind of ignore that. But they've collected data on the number of pets that folks have, and then they have the frequency or the number of times that piece of data occurs in the set. So you can see that there were 4 reports of having no pets. There were 2 reports of having 4 pets in the home. So we're just able to see the number of occurrences of that particular quantity or data point in our data set. So a few things to notice. On this side over here, notice that every possible outcome, you have to list them all, okay? You can't just go 0, 1, skip 2, and then go 3, 4. You can't do that. If 2 is an option, if it's a possibility, you have to include it in the table, okay? So even if, I mean, this data shows that 5 people said 2. Let's say maybe, what if 0 people said 2? Can you just leave 2 out? No, you cannot. You have to include it. You have to include all possible options. If we look at this one, there's something glaringly wrong with this frequency table. We look over here and we see all the frequencies, and that looks really nice. And then we look on this side, and this is a data set where they said, you know what, I don't want to have 50 different squares. So I'm not going to go 10, 11, 12, 13, 14. I'm going to bracket this off into quantities, into sections that have this equal amounts. Okay, but if you look, the problem here is 15 is on both sides. 20 is on, so is 25. So what happens if somebody has 25? Where does the count go? Does it go here or does it go here? Okay, so this is a terrible example of a frequency distribution table. It can't look like that. Okay, you would want it to look like this one. That gray you can't really see. You'd want it to look like this one. Okay, 6 to 11, then 12 to 17, 18 to 23, 24 to 29, 30 to 35, and then 36 to 41. And you can see the frequency or the number of times that a piece of data fit into that range. And then over here they have the relative frequencies, which all the relative frequency is you take the frequency, the number of times the thing occurred, and divide it by the total number of points in the data set. So this one just happened to be 100, so it makes it look like nice little clean decimals. And that just gives you the percentage, and we'll learn about this later, it's also the probability of that number occurring within the set of data that you have. So that's a little peek into frequency distribution tables. It's one way to look at the data. I prefer to take the data and make it into graphs, either bar graphs or histograms or graphs that look like this. Now, these graphs, and this is really important, these graphs have smooth curves, okay? which means that the data we're dealing with is continuous. Over here, number of pets, that's not really a continuous piece of data because there are jumps. You jump from 0 to 1, from 1 to 2. You can't have 2.5 pets. That would be morbid. But these graph types are continuous because they have the kind of the smooth curves. And then there are different shapes, and we talked about these shapes in some of the discussions. The red one here in the middle is there's no skewness. It's symmetrical. It's normal in shape. It's a bell curve. Okay. And the point here is we're looking for symmetry. We have these guys over here, the green. I probably should have drawn that in green. I've got a negative skew, okay, which means that it has a tail over here on the left on the smaller numbers. So they call that negative skew because you have that tail on the left. And that tail on the left, right, these guys are all outliers, okay? Most of the data is right here. But then you've got these little numbers over here, and that's going to mess around with mean, median, and mode, and we'll talk about that in a second. Then the other one is you have the positive skew, which looks like this, and you've got outliers over here on the larger number end. That's why they call it a positive skew, okay? And so the example that I like to look at and think about with these types of graphs is if you were to look at the grades of the class, which shape would be best for the students? Really kind of best for everybody, but especially best for the students. Would you want to have a positive skew, a normal curve, or a negative skew? Me, in my personal opinion, I would rather have the negative skew. I mean, I know it says it's negative, okay? But look at this, right? This means that most of the grades are high, and you've got a few low grades over here. If your grade had a normal distribution, right, then you have most of the grades bunched up in the middle and a few over here that were good and a few over here that were bad. You definitely don't want a positive skew with most of the class piling up over here on the lower grades with only a few of the class getting the higher grades. So kind of something to think about. Well, look at that. All right. Measures of central tendencies. So these are statistics that describe either the sample or the population that we're dealing with, okay? And they're meant to define or to give the reader or whoever's looking over the data a sense of where the bulk of the data is, okay? So the mean, it's your classic average, right? Add up all of the data points that exist in the set and divide by the number of data points that there are. It's your classic average calculation. It's the mathematical center of the distribution, okay? The median is the middle of your distribution, okay? It is the number that is in the exact center, okay? So it's like you take all of your numbers, line them up, and you start moving in from one end and moving into the other end until you get to the very middle, and whatever number is sitting there at the exact center, that's the median, okay? That's how you find it. This is also defined as the 50th percentile. That says percentile. The 50th percentile, okay? Which means that so whatever this number is, half of the scores are below it and half of the scores are above it, okay? Last one is the mode. And that's just the number that occurs the most, okay? So the mode can be tricky, right? The mode can throw you off. You might have a number over here that repeats a bunch, and it'll make the mode look like it's on this side. That would be a positive skew, by the way. But anyways, so I have these 3 different measures of central tendencies. So how do we know which one to use? Okay, well, it depends on the shape of the distribution and the type of data we have, right? We've got the nominal, the ordinal, the ratio, and the interval data. Okay, for nominal, the only thing you can do is mode, right? You can't order things, so it doesn't have a median. It doesn't have a number associated with it, so you can't calculate a mean. Ordinal, you can use the mode, what thing occurs the most, and maybe it also might make sense to use the median as well, right? If I can line things up with an inherent order, I can count and find a middle, okay? So maybe the median makes sense for ordinal as well. The last one's ratio and interval. They normally go to the mean, but you might not want to use the mean, right? Maybe you want to use the mode, okay? If there are some outliers that are pulling the mean away from the bulk of the distribution, then maybe the mode is going to be the way to go. Or maybe when you look at the distribution, maybe the median does a better job of describing the bulk of the data. Okay, that's the job of measures of central tendency, okay? So what does the distribution look like, and what type of data do we have, okay? That's how we decide. Oh, check this out. So I have my negative skew, right? Because I've got these outliers over here on the small side. And look what they did. I guess I don't have a reference, but if I had a normal distribution, right, the mean, median, and mode are all in the same place, right in the middle, if it's normal, okay? Those numbers are all the same. But if I have outliers, like these guys right here, notice, look what it did. It pulled the mean towards them, because the mean is it's a mathematically calculated thing. So if I've got a bunch of really, that's not even a bunch. If I have some smaller numbers that are hanging way out here, that's going to pull the mean away from the center, right? This no longer does a great job of describing the bulk, okay? So I've got the mean over here, then there's the median, and then the mode is still that most frequently occurring number right there. And then the opposite happens with the positive distributions, right? These outliers over here pull the mean in the positive direction, okay? That's why this is a positive skew, by the way, because the mean has been skewed to the positive direction. Or over here, the mean has been skewed, pulled in the negative direction, okay? Measures of variability. So this is last week's stuff. Range, variance, and standard deviation, okay? So I tried to make a point in the discussions with the questions I was asking people. I wanted folks to think about, if all you had was central tendencies, right? If all you had was the mean, that really doesn't tell you a lot about what the population is like. You just know, okay, I know where the average is, I know where the bulk of people are, but then you have no clue, you have no idea what the distribution, what the data set is like around the mean, okay? That's where these measures of variability come into place, okay? So the range, you just take the biggest number in the data set and subtract it from the smallest number in the data set, okay? And that'll give you the range. It lets you know, well, I don't know any other word for it but range. It lets you know, like, how wide is the spread, okay? The variance, on the other hand, this is where we start to look at what the spread is like, what the distribution is like, okay? And for me, looking at the equation for variance helps me to figure out and think about how this works and what's going on. So when you're calculating the variance, you're going to take um, the numbers in our little data set. You're going to subtract it from the average. So x bar, that bar above the x means average. And I'm going to take that quantity and I'm going to square it. Okay, so these are the differences. Okay, I want to know how different. So I have all these different x's in my data set. Oh, look at all these different data points. Yay, they're all different. And I want to know how much do they differ from the mean. That's what this calculation does. Okay, how different are they from the mean? And that's going to give me a bunch of different results. Okay, and then, I mean, I could just take those differences and then sum them, add them up. Add up all the differences from the mean and see what happens. Well, if you were to just do this, you'd get 0 every time. And the reason why, if you look at a distribution, and here's the mean, you've got mathematically the same amount on the right as you do on the left. Okay? These ones are all going to give you negative differences. These ones are all going to give you positive differences. And then if you add up all of those negative differences and those positive differences, it'll add to 0 every time. So that tells us nothing. So some really smart mathematician said, well, I know a way to get rid of the negatives here. If I square this, then the numbers inside of here that were negative become positive, and then I can go ahead and add everything up, sum it all up, and it'll make sense, right? All of these distances, all of these different distances from the mean will add to something, not 0, some number. And then I want to know, okay, so I've got all the squared differences from the mean, and I've added them all up. And so then I want to know, okay, well, what's the average, right? What is the average distance there? And so we divide by n, which is the number of numbers in my data set, n. And if this was a 3x4 grid, which I tried to draw, but I got really sloppy in that corner, that number would be 12, right? Now, sometimes you see this instead of written as n, you see it written as n minus 1. You only ever use n minus 1 if you're trying to estimate a population. Okay? If I've taken a sample and I'm trying to find the standard deviation of my sample that I'm going to use to estimate the standard deviation of a population, then you use n minus 1. It's for estimation purposes. Okay? And then standard deviation right here is we're looking at this and we say, okay, I squared all these numbers and that kind of inflated the value. So I'm just going to take the square root of whatever this is to get rid of that square. And that's what I call the standard deviation, right? The square root of the variance. And what it does is it eliminates that square, and it also returns my units. Because over here, the units of variance are squared. And that doesn't make any sense. I don't want my units to be squared. I want to get rid of the square on the unit so that the units are back in the normal units of my study, right? If we're measuring temperatures, I don't want to know what the variance is of temperature squared. I want to know what the variance is of just the regular old temperature. So you've got to take the square root to get rid of that. That's what the standard deviation is. It's just the square root of the variance to eliminate that squared bit. All right, so check this out. I have these normal distributions, and each one of them have a mean of 0, right? An average of 0. But they all have a different standard deviation. And so I want you to look at what these standard deviations mean, right? So this one, the blue, has a standard deviation of 0.7. It's my smallest standard deviation. And if you look at this graph, it's still a normal curve. You see the symmetry, right? But everything is all of my numbers, they're not very far from the mean, right? They're really close, okay? I've got a tall, narrow distribution. That's what the standard deviation tells me. That's why measures of variability are so important, because there's so much information hiding in there. If you look at the red one, right, this is my largest standard deviation, 1.5. Look at how short and stout that is, okay? These differences, this data is really spread out, okay? That's what it means when you're looking at standard deviations. It's telling you how closely are the numbers grouped around the mean, okay? If the standard deviation is very small, that means you've got a tall, narrow distribution. Most of the numbers are really close to the average. If your standard deviation is big, that means that most of the numbers are really far from the average, okay? It's really spread out data set. And that may mean good or bad things. Most of the time in a statistical study, we're trying to have samples that have smaller standard deviations. In most cases, not every case, but in most cases. All right. So we've talked that over a little bit. Let's calculate some of these things. So I have a small data set that I made up. So it's like number of pets in a home, and I've got these numbers here. So the first thing that I'm going to do, or that I like to do, is let's actually write them in an order that makes sense, not just in the order that the data gave me. So really, so I've got 0, then a 1, let's see. Oh shoot, I changed one of these ones to a 2. I'm going to do that here. Sorry everyone. I'm changing one of those ones to a 2 so that there's only 1. And then I've got 3 2s, 1, 2, 3, and then a 3 and a 4. So let's see, there should be 7. 1, 2, 3, 4, 5, 6, 7. Okay, those are all my numbers. And this one magically turned into a 2. And they're all lined up in order from smallest to greatest, okay? So now, if you're looking at this, well, what's the mode? Well, the number that occurs the most is 2, so the mode is 2. What is the median? Well, if I count in from the outside, I land right here. The very middle of my data is 2, so the median of this data set would be 2 as well. If I needed to calculate the average or the mean, I would add everything up, so I'd have 1 plus 2 is 3, plus 2 is 5, plus 2 is 7, plus 3 is 10, plus 4 is 14. So I would have 14, and there are 7 numbers. So, oh, look, the mean is 2 as well. That is crazy. That's why I had to change this 1 to a 2, because I wanted it to divide to something clean. Now, a real statistician wouldn't fudge their numbers like that, but this is made up data, so I fudged my number. And then just forgot to change it in the slide. Anyways, so I got the average as 2. Awesome. So we can calculate those things really pretty straightforward. What's the range here? Well, if I take the largest number and subtract from the smallest number, right? So the range, right, 4 minus 0 is 4. So the spread of the data is 4. And then, okay, so now this is where things get tricky. Let's calculate the variance. Okay, so I know that my average is 2. I already calculated that. And my equation for variance says that I'm going to take, well, let me write it up here. Well, so the first part of it is x minus x bar, quantity squared. So if I line up my little data points, so if I take 3 minus 2, 2 minus 2, 2 minus 2, 0, oops, 0 minus 2, and 2 minus 2, and 4 minus 2, and then 1 minus 2. So let's see, that's 1, 2, 3, 4, 5, 6. Okay, I've got them all. All right, so let's see, what is this thing? This is going to be 1. This is going to be 0, 0, negative 2, 0, 2, negative 1. Okay, So I've done this part. All right, now I need to square everything. So 1 squared is 1, 0 squared is 0, 0 squared is 0, negative 2 squared is 4. Notice that pesky negative sign went away. 0 squared is 0, 2 squared is 4, negative 1 squared is 1. Awesome. Okay, so I squared everything. Okay, then the next step here is I want to add up all of those deviations. All of the squared deviations from the mean, let's add them up. So 1 plus 4 is 5, plus 4 is 9, plus 1 is 10. So the sum of the squared, oh, my computer screen went dark. I really hope in the video that that wasn't dark for everyone. I'm going to assume and hope that it wasn't. I'll have to go back and watch. If not, then you can hear me and you can see all of the calculations that I've been making. But I walked through each of these calculations, and here in green you can see these are my sum of the squared deviations. Then add them all up to get that the sum of the squared deviations is 10. Okay. And now I need to divide by the number of things in my data set. So 10 divided by 7 is approximately 1.43. Okay. And I put that approximately sign there because I rounded it. It was a decimal that went on for a long time, and I didn't want to write all the decimal points. And so that's the variance. But it is a squared quantity. It is not in the original units. This is number of pets squared, which means nothing. So then take the square root of that thing to get the standard deviation. And my final standard deviation for this sample is 1.196. Okay. Which means that on average, any given data point in this set of data differs from the mean by 1.96 pets on average. Okay, it's the average difference from the mean of any given number in the data set. That's pretty cool. Okay. Okay. Populations and samples. So we talked a little bit about populations already, right? A population is some nebulous group of individuals to which a natural law applies. Okay, and I'm trying to figure things out about them. In most cases, these populations are far too large. There's no way you're going to talk to every single person in the population. Okay, so for example, let's say that you were studying. Let's say that your population was high school sophomores in the United States of America. Notice I've already made some huge limitations. I'm looking at just the United States of America, and I'm looking at just high school sophomores. Is there any way that anyone is ever going to be able to talk to every single high school sophomore in existence in the United States? No, there's not. You can't, right? You're not going to get to them all. So what we do is we take a sample, right? I go through and I grab at random. And that's the really hard thing, is you have to make your selection of these people truly random. Everyone needs to have a chance of being selected. And then you randomly pull out people from that group. And so instead of talking to everyone, maybe you just talk to 1,000 of them. But you truly randomly selected them. And so you've got a sample that you hope reflects what the actual population is like. Okay? And that's kind of where we're going with this. And that's where, so this is kind of pointing us towards the end of the class, right? This sampling is so important because you've got to be so careful that the sample that you've taken actually represents the population you want to study. And the way that you do that is, number one, everyone in the population has to have an equal chance of getting sampled. Okay? If they don't, then your sample is biased. And then, so if everyone has an equal chance of being sampled, then you need to, in a perfectly random way, pick individuals from that to then represent the entire population, right? So then I have this little sample that is supposed to be a representation of this, and I can take this sample and I can calculate all of my statistics, like the average or the mean of the sample. You can get the sample standard deviation, and then we're going to do things to check how close do those things, what is the probability of those things matching what the actual population was. Like, that's where we're going, okay? That's where we're going with this. The other thing, so Z-scores come up in Module 5. This is the new material for us, okay? And what a Z-score is Z equals, you take any number in your data set, right? So there's your sample. I'm going to pull out a number X, and I'm going to subtract it from the sample mean, and then I'm going to divide it by the sample standard deviation, okay? And it's going to give me some number that is unitless, and it's either going to be positive or it's going to be negative, and then that's going to tell me how far away is this number from the mean, okay? So, right, here's my graph. Here's the mean right here in the middle. This one centers around 0, and these numbers down here represent standard deviations. 1, 2, 3. So all these numbers are 1 standard deviation from the mean. These numbers are 2 standard deviations from the mean. These numbers are 3 standard deviations from the mean. And notice, very, very few numbers can be 3 standard deviations away from the mean. That's a really, really unlikely thing. And the positive and negative bit of this tells you if you're to the left or to the right of the mean, okay? So let's say you calculated something and it had a z-score of positive 1.5. That means that that thing is 1.5 standard deviations away from the mean, okay? You're 1.5 standard deviations away from the mean. And if you look at this, right, 68%, okay, and now this is for normal curves. This is for data that is normal, okay? That's really important. 68% of all the data will be within 1 standard deviation of the mean, either -1 or +1, okay? 95% of all of the data will be within 2 standard deviations of the mean, and 99.7% of the data will be within 3 standard deviations of the mean. Okay, so if you know a thing's z-score, then that tells you a lot about where it is in the distribution and how likely that number is to occur in your distribution. If you have something that has a z-score of 3.1, then that is a piece of your data that is very, very unlikely. The probability of you getting that number is very, very small. But if something has a standard deviation of like 0.1, then that thing has a really high likelihood of occurring within the sample, okay? That's what z-scores are about. Very last thing to look at today, and this is kind of like peeking into the future a little bit, but sampling distributions, what they are is, here's my population, and there's all these things that I want to know about this population, and I'm going to take random samples, just the way that I described before, and I've got these, so here's random sample 1, here's random sample 2, here's random sample 3. And these samples, oh man, these numbers are the worst. 3, I'm getting sloppy. 2, right, these I randomly sampled from everywhere inside. This, we'll call this the blue sample. I randomly sampled from everywhere inside. The green sample, we randomly sampled from everywhere inside. I'm going to calculate an average, right? This is average sample 1. This is the sample average 2. This is the sample average 3, right? So I have my whole population. I sampled it 3 times randomly, and because these are random numbers, these averages are not going to be the same, okay? And what a sampling distribution is you pretend that you do this an infinite number of times. You sample this thing infinity times. And so you have an infinite number of these uh, average means. And then if I take them and plot them out onto a distribution, you're going to get a perfectly normal curve whose average is the actual average of the population. And then your sample averages will appear somewhere in the distribution, right? Maybe this one is here, maybe this one is here, maybe this one's over here, right? And wherever it occurs within this lets you know how likely that average is. Whoop, and there's my screen going dark again. How likely that average is to be in that population. More to come on this idea later. Just kind of wanted to give you guys a sneak peek. Study hard for the midterm. Look over the notes. Look back through the discussion boards. You can watch this video. Email me any questions you have. You guys are going to do awesome. Thanks for everything, and I will see you guys in the discussions.